So this is a quick primer on getting valence electrons. So when we talked about our electron orbitals, we had a diagram that was much shown as we've got up there, and we don't need these rules, so we'll erase those. So what we're doing is placing electrons into our electron orbitals, and we're getting our homes. So if we picked something like hydrogen, it has one electron, it goes into the 1s orbital. If I was to write that information out, I don't want to have to draw this big colored diagram each time, so I would just say where it went. Well, the first electron for hydrogen went in the first energy level. It was the s-type orbital. So I'm now naming where each of hydrogen's electrons are. If I now switch to say something like helium, well, now what happens is helium has 2 electrons. Well, I want to specify where each of those 2 electrons is. I still have that electron that came from the hydrogen one, if you will, and my second electron would go into the first energy level, s-type. Okay, this would get a bit redundant to write out each time, so one of the things that we'll do is we'll go through and simplify and drop it to 1s2. Okay, so now what we're going to go through and do is actually level this up a little bit more complicated, and let's pick a much bigger structure. Okay, so the structure we're going to pick there, well, not that much bigger. We'll go with something like carbon. Okay, and if we were to evaluate carbon, well, carbon has 6 electrons. Okay, and one of the assumptions we're going to make is that we're starting it as neutral. So let's place those 6 electrons. In our diagram, we would go something like this. Okay, there are 6 electrons. The first electron went into the 1s, the second electron went into the 1s, the third electron went into the 2s, the third or fourth electron went into the 2s, fifth into the 2p, sixth into the 2p. And again, this is that redundant form that gets really tedious to write out, so we could simplify this down and call this 1s2. That superscript is now referencing the number of electrons, okay, in that orbital. We would have 2s2, and then we'd have 2p2. Okay, so we could condense it. Relatively nice and simple. What we just specified was the electron configuration for carbon. What you'd be expected to provide for that electron configuration is this thing, okay, in the red box. The green part is like the show your work, if you will, if you really wanted to go that far. So we want to address some kind of aspects behind this. Number one, the periodic table has this information encoded in it. And I think I can pull up a periodic table here, but I'm going to lose my work. Okay, so what we'll do is point this information out. Okay, first and foremost, the number in front in our configurations was the energy level. Okay, as we talked about in class, the energy level is the row, period, series, whatever you want to call it, or not whatever you want to call it, row, period, or series on our periodic table. Okay, the next point is the letter. This is the name of the block. Okay, so the block on the periodic table, and I'm just going to do PT. If we look now to our electron configuration where we specified it a little bit better, that number as a superscript is the column of the block. Okay? So if you can, hopefully you've got solid notes and you've got this written down, because what I'm about to do is now disappear it and take a look at a periodic table, which I'm hoping I can pull up relatively easily here, but let's go through and see. Cool, periodic table. Let's take a look for our carbon. Okay, here's our carbon. I hope that shows up somewhat okay. So there's our carbon, attempting to highlight it here. Okay, so now what we want to do is think back to that electron configuration. The most important thing for you to be able to do is to identify where the last electron goes, and we'll talk about why here in a second. Okay, so let's address where that last electron goes. Well, if we look at carbon, it is in the 1, 2 second energy level, which means that last electron goes into a 2-type energy level. Okay, carbon is found in the P block. I'm going to use the white erase here to represent it. This whole area over here we called the p block, okay? Which means if we're looking for the last electron for carbon, it's going into the p block. So the last part of my electron configuration, okay? Next step, which column is it in? Okay, well, it is in the 1, 2 second column of the p block, so I would write 2p2. Okay, I've now specified the very last piece of my electron configuration. Okay, if you can get that, you can eliminate lots of multiple choice answers, okay, on a test. You are officially responsible for filling out the rest of those electron configurations. And there's a variety of ways we can go through and do that. I've got the sequence memorized on how they fill, so I can come up with it pretty quickly. Okay, so 1s2, 2s2, 2p2. Okay, note the superscripts, when we add all those up, what do we get? We get 6, 6 corresponding to, my periodic table looks a little weird, okay, the atomic number for the element, okay, so the number of electrons. Okay, what we now have is an electron configuration. Phenomenal and fantastic. Okay, so now let's backtrack all the way back to our other thing here. Okay, I'm going to pause. In the very next section, what we do is move into bonding. Well, in bonding, it's how electrons are shared between atoms. Well, which of carbon's electrons are the most likely to be shared? Well, the ones furthest out, the highest energy electrons. So that statement gives us our answer for what are our highest energy. We need to look for the highest energy level. The highest energy level here is 2. Are these electrons in a second energy level? Yes. Are these? Yes. How many are in the 2s? 2. How many are in the 2p? 2. How many valence electrons does carbon have? 4. We now have our valence electrons. Now we can use that information in Lewis structure. Okay, let's pull it with, again, a slightly more complex example. So complex, sorry, as I flip through, look through, chlorine. Okay, chlorine, and magic of video, ta-da! What you should be able to do very quickly is look at your periodic table, and so now I'm going to delete all that, so much for the ta-da, is look at our, look at our periodic table, find chlorine. So it's a good thing that you've been doing all those cryptograms that Greg has insisted on, because now you can find the chlorine quickly. We look to see where chlorine is. It's in the 1, 2, 3rd row. 3rd row means its outermost electron is in the 3rd energy level. It's in the p block. It's in the 1, 2, 3, 4, 5th column, 3p, 3p, 5. Okay, the rest fill up. So how many valence electrons does chlorine have? Well, highest energy level, our energy levels are 1, 2, or 3. 3 is our highest energy level. The 3s holds 2. The 3p holds 5. I get 7 valence electrons. I can now use that in Lewis structure. For those of you being like, God, I have to draw out whatever this is, an electron configuration every single time? No. Here's the next massive clue for how you can get the valence electrons very, very quickly. If you remember, we said carbon had 4 valence. Okay? Look at the Roman numeral in the column where carbon is located. Okay? I know that's really hard to see, so I will write it a little bit bigger. It is IV. What is IV in Roman numerology? Ugh, that was awful, but whatever. It's 4. What does that correspond to? The valence electrons. Okay? You might be saying Mike's full of crap and just making up random numbers. Chlorine, in an entirely different row of the periodic table, take a look at its column name. It has the Roman numeral VII, which happens to correspond to, Holy Mother of God, 7 valence electrons. The Roman numerals in your column, wherever your element is located, tell you the valence electrons. Okay? We'll talk about what that means as far as the patterns that we've talked about in our periodic table on Monday, but really I wanted to make sure you knew how to identify your valence electrons at least 2 ways. Looking at our electron configurations and the flip, pulling them directly off the periodic table. Okay? With that, thanks for listening. See ya Tuesday.